So we are trying to understand, because I saw phi plus, phi minus, so I thought I might explain to you that phi plus would always involve any relation operator, phi minus would involve a creation operator. Okay. Now, so if I would calculate, let us say the Hamiltonian of this theory, field energy, field momentum of this theory, I might explain in the same context before rubbing it. Let me just explain that X is K mu, X mu is K0, X0 minus Kx, same the e to the power plus minus ikx, where this Kx is K mu x mu actually, the product of 4 vectors. All right. And so and how are the two related? So P mu H cross or K mu. So this is the momentum, this is the wave vector. Okay. So you have your standard P equal to H cross K, and P0 equal to E by C would be H cross K0. This would be H cross omega K by C. Okay. So this would follow these things, and but your P square would be your M square C square. This would be P mu. This would be your E square by C square minus vector P square. You can express, relate E by C by E by C is your either let me put H cross K0, but why am I doing it? You can correlate P with this, and this would be your P is H cross K. Okay, so P square is H cross K square, or H cross K mu, H cross square K mu, and this would be your E square by C square is H cross omega K by C, E square by C square, H cross square K0 square minus H cross square vector. This is much simpler. Okay. So I mean you can relate any quantity with any quantity. The only relation, this is the only defining relation. Okay, in your Fourier space decompositions. And why do I call them Fourier space decompositions? I will come right now. Okay. So here omega K is square is then K square plus M square C square. Okay. And if you take only the positive part, positive energy part, then this is now what I would like to explain is using these are just conventions or notations in this one. I can express my field energy and field momentum in terms of the like H, we define N of K as a dagger of K A of K, we define it like that. And this we will call as the number operator or the number density. Okay, why would we call this a number operator is one thing. And then Hamiltonian would be this, would be sum over vector K. We are doing with now with finite vertical summation, okay, not integration. So this H cross omega K times N of K plus 1/2. And so vector P would be P, the density, dqx. This would be also summation over vector K and H cross K times N of K. Okay, and if you like, you can write K and H cross K alpha N of K. So let us try to understand what these expressions mean. I have not derived them. If you like, I would tell you how to derive them. Okay, because similar things we would also do in string theory. But right now my aim is to get the physical meaning out of it. So given a theory like this, defined by this L, 1/2 d mu phi minus 1/2 n square phi square, and defining the Fourier expansion of the field phi in terms of the positive and negative frequency modes using the annihilation and creation operators, and going through a little bit lengthy procedure but a very simple procedure. One can calculate the Hamiltonian, the field energy, field momentum, or the force field momentum. So its zero component is H and it's the spatial components of field momentum. So and this you arrive at from the this same expression that we derived canonical Hamiltonian density using the Legendre transformation. So we have to put back those Fourier expansions there and calculate term by term, right? Making term by term calculation, finally you end up with this result. It is essentially it's one result, okay? These two equations are just the component equations of this equation, right? Now, so you have only one field phi, therefore you have only one number density operator n of k, and this is a product of a dagger of k times a of k. Supposing I have two fields, then I would have n1 equal to a1 dagger a1 and n2 equal to a2 dagger a2, right? So in the first place, my aim is to explain to you, then if you would like, I would also give you a derivation of this, okay, or the steps how to do it. But the first thing that we want to understand is this physical meaning, because we would arrive at a similar, we want to arrive at similar results for our string theory case, okay, following simple steps. So let me here tell you now little more about, supposing I have, and this 1/2 factor of 1/2 is nothing but the so-called 0-point energy or the normal ordering constant. In string theory, you will have mu, which goes from 0 to 25 for bosonic string theory. So here the dimensions of the string theory would appear, okay, because mu would take 26 values, 0, 1, 2, 3 up to 25, okay. So that is one thing, and that's a very interesting result. I will tell you next time. But supposing I have another field theory, let me call it L1, let me call it L2, d mu phi star d mu phi minus m square phi star phi. Then here for phi, I would have a decomposition of this summation and this coefficient, summation over the vector k. But here now I would have a of k e to the power minus ikx plus b dagger of k e to the power plus ikx, and making use of this, so phi dagger would be this now it would be b of k e to the power minus ikx, and transconjugate of this would be a dagger of k e to the power plus ikx, right? So for this theory, let me make it dagger, okay? So d mu phi dagger d mu phi minus phi dagger phi, okay? If I have this, then the Fourier decomposition that I use would be this. In string theory, in the colloquial language, they always call it Fourier modes of string theory, Fourier modes. In this, I'm much more used to calling it Fourier space decomposition, and I know why it is called a Fourier space decomposition, because I would calculate and show to you that this is just a diagonal matrix, and also that n of k, you can prove it explicitly that n of k commutes with n of